Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on February 2nd, 2026, just about a week ago. It introduces a training paradigm called revision, which demonstrates that 2 million unpaired text samples can actually outperform a baseline trained on 1 million real image text pairs, effectively substituting expensive data with cheaper alternatives. The paper is titled Modality Gap-Driven Subspace Alignment Training Paradigm for Multimodal Large Language Models. And as we'll see later, the implications for efficient model scaling are really impressive. To understand the challenge, Figure 1 illustrates the phenomenon known as the modality gap. It shows that even when text and images share the same meaning, their mathematical representations land in completely different regions of the vector space. The red cluster on the left represents text, while the blue cluster on the right represents images, and they are separated by a systematic offset labeled stable bias. Crucially, the internal arrows mark anisotropic residuals, which means the data spreads out in specific directions rather than forming a simple, uniform sphere. Because prior methods often ignored this complex shape, they struggle to align the modalities effectively. Figure 2 digs into the geometric statistics that validate the author's theory about this gap. In panel A, the blue leakage ratio tracks the red bound closely, confirming that gradients stay confined within a specific task subspace. Moving to panel B, we see the bias is stable, where the high stability curve indicates the gap's direction evolves passively rather than fluctuating wildly. Then, panel C focuses on the semantic subspace, where the high condition number reveals strong anisotropy, meaning the data cloud is stretched out rather than spherical. Finally, panel D proves that the remaining noise is orthogonal to the bias, so these two error sources are decoupled and can be treated separately. So, Figure 3 lays out the ReAlign pipeline, a method to mathematically force the text and image distributions to overlap perfectly. Starting from the separated states in Panel A, Panel B shows anchor alignment, which shifts the source distribution to overlap with the target center. Next, Panel C illustrates trace alignment, scaling the source variance to match the target's energy. Because spherical projection causes a secondary shift called phantom drift, Panel D applies a centroid alignment correction. This leads to Panel E, where the modalities are finally perfectly aligned. Alright, Table 1 now quantifies how these geometric strategies translate into actual performance gains. The rows compare baselines, like the isotropic C3 method, against revision at the bottom. In general tasks such as real-world QA, revision hits nearly 48, clearly surpassing the unaligned model's 43.5. This trend continues across reasoning and hallucination benchmarks too. As a result, the final column confirms revision takes the lead with an average of 51.16, efficiently outpacing C3's 48.06. Okay, Table 2 takes this a step further by asking if cheap text can replace expensive image-text pairs. It compares revision against unicorn and a standard paired baseline, labeled with image, tracking both performance and data cost. Looking at the final columns, Revision 2M achieves an average score of 49.75, which actually beats the paired baseline's 48.91. Crucially, it does this with a cost of 0.74, meaning it is 26% cheaper than gathering paired data. Meanwhile, Unicorn lags behind at 43.94, showing that simple mean shifting isn't enough to bridge the gap effectively. Well, Figure 6 visualizes the actual manifold alignment using PCA, which projects the complex, high-dimensional data into visible clusters. In Panel A, the original text in blue forms a distinct group that is completely separated from the red image modality. Next, Panel B shows the C3 baseline, which expands the text distribution with noise but fails to overlap with the visual data. Finally, Panel C demonstrates that ReAlign successfully shifts the text into the visual support region, achieving a mixing rate of 4.35%. Wrapping up, two takeaways stand out. The modality gap is a structured geometric problem rather than random noise, and cheap unpaired text can effectively replace expensive image text pairs. This offers a robust, cost-efficient path for scaling future multimodal models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.